Hello.
Here.
Yes, I'm here.
Yeah, we don't see you yet.
Yes, okay. I'm just trying to push my stuff. Yeah. So controllers.
Well, we see your screen, but not the talk.
Do you see it? Hello.
Not you. Yeah, now, perfect.
You see it?
Yes, we do.
Very good, very good. Okay.
Okay, so let us start. Let us welcome Jerzy Lukierski, and yeah, you see his title of his talk. So Jerzy, please start.
Okay. Okay, thank you very much. I'm sorry I'm not at the place, so to say, but I got some small problem with my throat, so I'm at the distance. So my talk has a title as you see it now. I would like to say about some, I would say, kind of new approach to Snyder type models, where you get also quantum spinors in the business. But for that purpose, you should, in principle, use super algebras. So now you see this is the list of my questions which I'm going to discuss. So at the beginning, I'll say about the quantum deformed space-time models, some short resume. After I'll show you that a kind of main I would say point which one gets when one uses the Snyder model. And my point is that this thing, which I call Snyderization, can be used to various Lie algebras and superalgebras. So I'm going to kind of generalize a look at the algebras from which you can construct Snyder model. And in the points 3 and 4, I'll discuss the Snyder models which are supersymmetrized. And I consider Young model, which is just Snyder model is related with the 5-dimensional in D equal 4 with 5-dimensional rotation group, and Young models are related with 6-dimensional Young rotation groups. So in the case of Young models, you have more. You have, besides the quantum space or superspace, you have also the momenta. Okay, so I'm passing to the next transparency. So what is the point? Why the use of Lie algebras here is a kind of a new one, because you put inside of the algebra described by the Lie algebra the something what I call quantum elementary system. It means I'm introducing the quantum group which is acting on the quantum space. So in the case of the kind of traditional Snyder model, quantum group is a Lorentz group, and quantum space is a coset 05 divided by 04. Now you can have also the quantum spinors, but in that case you have to deal with spinorial coverings. So you have here a small list of coverings of space-time symmetries, which you know, and you need this right-hand side if you want to introduce spinors. But the natural way of getting this spinorial coverings is just superalgebra, because in superalgebra this is the feature that you get. I mean, not in all, but in most of the superalgebras, you use the spinorial covering. So I'm going to be interested in such kind of quantum space-time, which are relativistic. It means covariant under the Lorentz group, which might be classical or quantum. Let me tell you about the most popular quantum spacetimes. I think the most popular is so-called DFR, from the names of Doppler, Frelinghuysen, and Roberts, quantum space-time, and this is just when the commutator is equal to some constant tensor. So in this case, you can provide H, which leaves this relation as a covariant by twisting Lorentz algebra. This is a kind of known abelian twist. Now you can introduce also non-abelian twists, and I did it in 2006 with my collaborator Mariusz Woronowicz. It's a kind of small Woronowicz. Big Woronowicz is in Warsaw. It's not the same one. And now I'm speaking about the big one. So the further generalization was obtained for the structure of quantum space-time in papers by Zakrzewski, Woronowicz, and Podleś. And what was the point there? That he was firstly describing all quantum Lorentz groups, which can be extended to quantum Poincare of algebras, and thereby discussing the modules of such structure. Then he obtained much larger class of quantum space-times. But this is a mathematical result, I would say. Now, another thing is a kappa-deformed quantum space-time. I have presented here the formulation which includes all kinds of variants of kappa-deformed quantum space-time. For example, light cone kappa deformation, where this constant 4 vector here is a light cone vector. So this is the first period where this things was studying. Very important paper is by Henri Rouek and Sean Majid, where they have just looked at kappa Poincare really from the point of view of non-commutative geometry, and they use so-called bicross product basis in which the Lorentz subalgebra is classical. Now, the third type of non-commutative space-time is due to Snyder. What is interesting that this construction is the first one, because it's in 1947 where there was introduced a model of quantum deformed space-time, and the algebraic relations look like this. So you have here the basic relation is here, where the commutator of x's is equal to is proportional to the generators of the Lorentz algebra. In Snyder case, this was the classical Lorentz algebra, and of course there is a standard covariance relation. So now such algebra can describe O for 1 or O for O32 equal for de Sitter and anti-de Sitter algebras. And the idea is the following, that you write this algebras, but from the generators which have one of the indexes is index 4, which is just outside of the Lorentz range of indices, which is 0, 1, 2, 3. So you make this kind of replacement when here this beta, which is here, is equal epsilon times 1 over r square. R is a ADS radius, and epsilon is for de Sitter plus 1, for anti-de Sitter minus 1. So as I mentioned, this idea can be extended to other groups as well as separate groups. And what is important that to define quantum deformed fermionic spinors, then you have to introduce the superalgebras where supercharges will correspond to quantum fermionic spinors. I mean fermionic, it means anti-commutative, because in quantum field theory we know that fermionic fields are anti-commutative. So now let us recall still the situation with Snyder model. So you have a decomposition of O for 1, which is de Sitter algebra, into Lorentz and the coset. And this part, which is the second part, I denote by S. I call it Snyderization procedure. It means that you make out of these generators the quantum space-time. So the Snyderization procedure is the replacement of the generators by non-commutative quantum space-time coordinates. So in this way, this algebra describes the whole quantum elementary system because H is equal 031, and this module is described by this constant. Now this construction can be generalized to any symmetric Riemannian pair. And here is the structure of symmetric Riemannian pair, where you perform the Snyderization in such a way that the coset generators, which are related with this K, and this you see from the from this relation that this is the coset, K is a coset, so symmetric coset. So you make out of this K, you may just some quantum space coordinates. So in this case, of course, we obtained H covariant quantum space from this Riemannian coset. Now one can also extend this Snyder model, this traditional Snyder model, in the equal form by adding additional space axis. This is an axis, I mean, fourth axis you add to Snyder model, you add to Lorentz algebra, the fourth direction, the fifth direction you add when you still have, I mean, two additional axis comparing with the Lorentz algebra, and this provides you with so-called Young model. In this case, the Snyderization, I mean, replacing of generators by non-commutative quantum coordinates, goes like this: that this there you have also the generator J, where the generator J is related with this rotations M4, 5, and you Snyderize just besides x mu what you have in Snyder model, also the momenta, the quantum momenta. And now when you just translate the algebraic structure of this 051 into this quantum elementary system, then you see firstly that this generator gives you this type of relation, which is written here in this kind of structural summary of the relativistic Heisenberg algebra structure, which you get from such a model. So you obtain this quantum space coordinates satisfying this kind of generalized quantum Heisenberg algebra, which is relativistic because all these variables are covariant under Lorentz algebra, x mu as a vector and j as a scalar. So this, what is interesting, in the same year when Snyder published his paper, Young also published this extension, which maybe in some kind of more generalized way I present here. So now the novelty in which I'm going to about which I'm going to discuss here is the description of Spinorial, Snyder, and Young models. So the best way is just to use some simple superalgebras. So the simplest case of such a Spinorial Snyder model would be to take just covering of O21, which is SP2, and take the superalgebra OSP12. And now you perform the Snyderization here on the fermionic coset. So you have here the generator. These are this is the three-dimensional Lorentz algebra, and these are the supercharges, just two of them, and you get in the Snyderization procedure, you get from Q, you get a spinor. So you obtain from this algebra, you get the following equation. And this is the kind of counterpart, Spinorial counterpart of Snyder relation. And this is, I would say, perhaps the simplest Spinorial Snyder model, which one can construct, and it is in d equal to +1 dimensions. If you take a covering of a Lorentz algebra, then you deal with SL2C. So you have the following, this is the holomorphic structure. So you make the following coset decomposition. And these generators are Snyderized in such a way that this super part is becoming a complex spinors. So you get, in place of this super relations here, you get this relation which describes you the spinorial Snyder model. However, Z is holomorphic, so you have to introduce also the complex conjugated relation, because this M describes just a self-dual part of the equal for Lorentz algebra. You know from the spinorial description of Lorentz algebra that you have to add still M alpha dot B dot. Now, another example is if you go to OSP14, where you describe the covering just of anti-de Sitter algebra. And in this case, the decomposition looks like this. And again, you get this is the structure here, and here I just listed those generators from this structure which are getting Snyderized. It means from this you obtain x mu, and from this you obtain xi. So you get a Spinorial D equal for ADS Snyder model, which looks like this, where here you have this is the general O32 covariance relation, which we decompose into Lorentz covariance expressions. This first expression gives you this thing which is related with construction of space-time coordinates, and this is just the part which you leave unchanged. MU are just the generators of a Lorentz algebra. Now, what is interesting that you can use also this super algebra describing Spinorial D equals 3 ADS Young model, but in this case you have to introduce three-dimensional space-time generators and three-dimensional momental generators in such a way. So the whole decomposition of the algebra looks like this, where you have still this D, which corresponds to this generator. This generator is a dilatation generator if you interpret O32 as three-dimensional conformal algebra, and so you get here just M, which is three-dimensional Lorentz algebra generator, and this is the O11 internal symmetry generator. These two things are describing the quantum phase space coordinates. Now you can go also further. You can obtain D equal for Spinorial Young model, but you should add to this OSP14. You should OSP14, yes. You have to add instead 1, 2. Why 2? Because you will have a 2. Two multiplets of supercharges, and one multiplet will correspond to the fermionic coordinates, and second to fermionic momenta. And this is these are the anti-commutators which you obtain from this structure. So you see, this describes you also a kind of quantum phase space, which is odd. I mean, so it's a kind of Grassmannian phase space where you have such relations. So you have also the bosonic generator here, J, which is related with the decomposition, where you have this algebra, it is a bosonic sector O2 times O32, and O2 enters here in this relation. So now, just the observation that if you wish to supersymmetrize Snyder model, one should add one fermionic anti-commutative spinor. And if you want to have supersymmetrization of Young model, you require the pair of fermionic spinors because you have to obtain the Grassmannian positions in momentum. And this thing is illustrated here on the superalgebra OSP14 and OSP24. Now I'm going to pass to supersymmetrization of D equal 4 Snyder models. I think the dimension of D equal 4 is the most interesting. By the way, in the literature, I think in some Japanese papers by Hatsuda, and so there were some remarks about something similar, but not related exactly with D equal 4 dimensions. So this is a kind of a new way of. I mean, this structure is not present in the literature. So now you can have, as far as D equal 4 Snyder models are concerned, you can have two such models. You can have a ADS Snyder model. You have a Spinorial covering of O32, and it goes to SPN4, and you can have a also the DS, D equal 4 DS Snyder model. But in this case, the Spinorial covering is a quaternionic unitary group. This quaternionic unitary group in complex notation is denoted by USP22. And after supersymmetric extension, then you obtain the following superalgebra in quaternionic notation. And this is the most clean notation, because there are also other notations for this algebra, but not so clean as here, where U alpha, it means anti-unitary. This is unitary, this is anti-unitary bosonic sector. So this is the description of this algebra as a superposition of two complex superalgebras. I have written this because usually one writes like this, but here this sector is linked with this sector. So if you use this, then the first sector will be related with first and second with second. So now this U alpha and H is just the anti-unitary symmetry sector, and this is in complex notation is this, and this is denoted by O star to N. This is the way of denoting, and the U alpha 1H. I mean this internal sector is equal to O2 for this superalgebras. Now, how looks the Snyderization of the situation in this situation? So you have the following decomposition of this thing here, like this, and here you have here this. This is the ADS algebra. This is the internal sector, and these are spinors. And now you perform the following Snyderization from these generators. You obtain the quantum ADS superspace. And now the basic relation, which is related, which is generated by the structure of superalgebra, is the following one, where you see that part of the generators of ADS stay as generators of Lorentz group, and parts are making X mu, and these generators are describing the internal symmetries. So this is the model which is ADS. The DS model, if you want to describe, of course, if you want if you use the quaternionic supercharges, you have two quaternionic supercharges, but dealing with quaternions is not so easy. So if you introduce just equivalent four-component complex spinors, they should satisfy so-called SU2 Majorana or quaternionic condition. Excuse me. Ela, zamknij pokój, zamknij okno, mi tu dmucha. Okay, so this is the SU2 Majorana condition, and you see that because of this condition, then you need only one supercharge, because you have, in this case, I is equal 1, 2, but from this condition follows that the QB2 is expressed by complex conjugated Q1. So because Q2 is expressed linearly by Q star, that Q star is basically not needed. So you use only one complex generator. So you have unrestricted 4 complex components. And now the basic relations of the equal and equal 1 ds superalgebra, which is written here, can be written in complex notation in the following way. So you have here the things from which you will make x mu, and this is Lorentz part, which remains as generators. This remains also as internal symmetry generators, and the Snyderization procedure is to the following quantum de Sitter superspace, which is here x mu ds, and you have a 4 component complex spinors and complex conjugated. So this is you have to take both because of this SU2 Majorana conditions, and the basic structure which describes this quantum superspace is described by the following relation, where here is psi, here you have x mu, and here you have mu nu as generators. Now I'm going to say a few words about the supersymmetrization of the equal for Young models. So we described in this a while ago DS Snyder model and ADS Snyder model. Now, when you add fifth coordinate to this fifth space coordinate to obtain the Young models, you might have all DS or O51 DS model or O42 DS model. And the same situation is here. You get or O42 or O33. So now this is related with the metric which you use when you add this fifth direction. So you have the diagonal component G44 is well plus minus 1, and you get 4 models here because you get G55 equal plus or minus 1. So in this case, you get here O51, O42 in these 2 versions, and O33. So I'm going to speak only about this O51, O42 models because O33 physically is less attractive. So supersymmetrization of O51 is based on the Spinorial covering, which is SL2H, where H is quaternionic. I mean, older people perhaps remember a guy which his name was Feza Gürsey, who was interested very much in this quaternionic structure. I had also in 80s a period when I was interested in quaternionic structures. So this in the complex notation is denoted as SU star 4. So now you supersymmetrize in such a way. So you obtain quaternionic superalgebra, which is equal to complex superalgebra, which is SU star 42. So now, by the way, what is this SU2 to an algebra? It is obtained by so-called wide trick. So you write the generators as belonging to the coset, this coset, and you multiply by I the generator. So in this way, you can link by this wide trick the Spinorial covering of O6 and Spinorial covering of O51. So this is the way of relating by this weak trick the D equals 6 Euclidean supercharges and D equal 5 plus 1 Minkowski supercharges. Now there is a structure which is related with this SU star 42. U star 42 describing the internal sector is the following. So now this is the algebra, which will after be inherited by this kind of generalized quantum deformed Heisenberg algebra. So I think I should write here I3, not T3. So I3, I2, and I1 are just the generators related with O21, and O2 is this A generator. So now, similarly, you can obtain so from this you can obtain the algebra which is satisfied by the variables describing the as I call it quantum deformed Spinorial complex of Heisenberg algebra. So the supersymmetrization of O42 Young ADS model is just based on well-known West-Zumino equal for superconformal algebra, which has in this. Sorry, you have some comment? Hello?
Just your time.
How much time? How much time? Hello.
Now you are at the end of your time.
Okay, so I'm really making it very short. So now let me just. So I'm saying that this is just the situation which we obtain in supersymmetrization for two Young model, and this is the Snyderization which you use in this algebra. So you get 8 complex quantum spinor components. Now I would like to, because this was the period which I was a little bit younger and I was interested with Anatol Nowitzki in this quaternionic business. So here is the list of our 4 papers where we discussed this super spinors and Euclidean superconformal and all the zeta algebras. I think 2 papers should be mentioned also. They are important because there are so-called ghost problem in the case of the zeta. So in these 2 papers, we just exposed this ghost problem. I think in the papers by Friedman quite recently, I think there is a kind of way out. Okay, so still 2 pages. So final remarks. So so now the main point is here in this presentation that I'm using the extension of a Snyder model to the situation with space-time variables and momenta using group theoretical or geometric method. However, in the original paper, Snyder, I added so-called by hand the momenta by postulating the kind of a general formula for these commutators, which also was assumed equal 0 in some variant, and for this commutator. And after one employs the Jacobi identity, this method works very nicely. You get a nice Snyder model with phase space. If you express a mu nu in terms of x mu p nu, you have just a model of a so-called Snyder quantum phase space. But this method, as far as I know, has not been extended supersymmetrically. Now, another thing is that you should be aware that if you speak about the algebras have a Hopf algebraic structure. So you have the following situation that you have 2 possibilities. You can use you can introduce 2 dual Hopf algebra describing O for one with the following assignment of the generators, another the following one. So when you have such assignment as here, with mu4 is equal p mu, then this is just the standard way of discussing the zeta algebra as describing curve translation generators. So one can say that passing from the standard description of the zeta algebra to the Snyder model is performing a semi-dual map where you keep the Lorentz generator the same, but you pass p mu into x mu. So by the way, this standard way was quite extensively used by Krajewski group in Russia, and this was from 1960. And this is a little bit on the side of Snyder model, but I think there's also the quantitative results. And now another story. I'm using here superalgebras, and if I use superalgebras, I'm getting spinors which are Grassmannian or fermionic. So if you want to have commutative spinors, you can also do that problem if you use the cosets of the groups which describe spinorial covering. For example, the famous Penrose twistors, which are d-equal for conformal bosonic spinors, can be obtained from the following coset. And this alternative choice, which is here, it describes a kind of fermionic twistors, which are obtained by the following coset of n equal 1 conformal superalgebra. And the last point is the following, that there is a question, of course, what does it mean, the generalized quantum deformed Heisenberg algebra, and still it is not so clear how to obtain this known form of canonical commutation relations by some limiting procedure or so. Because in Young model, in place of Planck constant, there is an operator. So this is a result of Snyderization of scalar symmetry generator. By the way, similar structure, which you find in Young model, was even applied quite effectively by George Zoupanos and his collaborators recently in order to introduce a new model of fundamental interactions. So that was I wanted to say, and thank you very much.
So, thank you. We are quite behind the schedule. So maybe, yeah, Adela?
Hello, Jurek. This is Fedele. In all your work, you are basically making a bundle, a spin bundle of these Snyder systems and generalizations. So you will have a Clifford algebra, so a Dirac operator, and then you would split this Dirac operator in a part, dividing a Dirac equation. There would be a part which is the usual one, but then would be some sort of derivative couplings or some generalization which would give a very interesting system probably. Have you investigated this, or you have any comment?
You see, I mean, we have in Poland some people who love very much all kind of bundles. I do not belong to those people, so I was using more a kind of group, I mean, algebraic point of view. But of course, you can look also in the following way, as you say. So I think, of course, for example, Andrzej Sitasz is a guy who could perhaps answer better than me on your question.
I'm not a bundle lover, but I'm a Dirac operator lover. But anyways, thank you.
Yeah.
Thank you. Thank you.
Okay, thank you.
Yeah, we continue now with Olaf Lechtenfeld.
Should I? Okay, I think. Okay, now it's.
All right. Hold on. Okay, I hope you can hear me. Yeah, first of all, I'd like to thank, of course, people who organize this always wonderful workshop, and
it feels doubly pleasurable to be here these times and to see so many people in the flesh, as I might say. What I want to talk about today is something that is based on a few papers we've done recently, and actually works from the early 80s. So, in fact, it's based on my PhD thesis. And so I feel really old now, coming back full circle to something I did almost 40 years ago. But through my defense, I can say I was dragged into this by Hermann Nicolai, who actually started picking up on that in last year. And since I'm one of the few experts in the matter, it was natural to join him in the enterprise. And it's amazing how you can rediscover things that you just missed in your PhD thesis. And, you know, it's been fun. So this has been collaboration with Sudarshan Anand, Hermann Nicolai, and PhD students Hannes Malcha of Hermann, Chetan Pandai and Saurabh Pant of Anand, and my own PhD student Maximilian Ruprecht. And well, I have to walk you through the definition of the construction of the Nicolai map first, because I don't think that everyone is familiar with that. And then I will focus on gauge theories, which is of special interest, of course. And then in the last part, discuss an application to the supermembrane, which connects to Hermann Nicolai's talk at the Humboldt colleague last week, because we have this joint paper and, well, there's this application. Yeah, I think it's fair to say that there are thousands, maybe tens of thousands of papers on supersymmetric Yang-Mills theory. And so I believe it deserves a look from a different perspective. And this is what this Nicolai map construction can offer. So let me begin with a simple example to make things clear. Just the Bessel-Mino model in Minkowski space, you have a complex scalar, a Majorana fermion, and an auxiliary complex field F. And here is the Lagrangian in Weyl notation. W is a superpotential, and here you have the relation between the fermionic and the bosonic couplings given by supersymmetry. Now let's integrate out the auxiliary fields, then you get this kind of Lagrangian. Here you have the superpotential derivative squared as the bosonic potential and the fermionic parts. Now, what I want to focus on is the effective scalar theory that you get by integrating out also the fermions, which appear only quadratically. Of course, they give you a determinant, which you can exponentiate back into the action. And so the action of this effective theory is now just a local bosonic part and a non-local fermionic part coming from this determinant. Okay, so I put an H bar here to show that this is one loop effect. Okay, this is ordered down by order H bar. These are fermion loops. So there's a bosonic part, SB, and a fermionic part, SF, which is non-local. And the G index here means this is happening at a coupling G. Coupling G is a parameter in the superpotential. Okay, think of something like G times phi cubed, for example. Okay, some coupling parameter. Doesn't matter what exactly it is. Now, I'm interested in correlators, quantum correlators of some arbitrary functional, bosonic functional, so functional of the bosonic fields phi at the coupling G, given by, well, either the original path integral or equivalently by the path integral inside this effective fermionic theory. So SG is the full action considering of the local and the non-local part. And because we have supersymmetry, we know that we don't have to normalize it, and the vacuum energy is 0. So partition function is 1. So the basic question that Nicolai asked and answered in 1980 is, how does this non-local theory remember that it came from a supersymmetric theory? Yeah, where's the trace? What trace of supersymmetry is left in this non-local theory? So there's some relation between the bosonic and the non-local fermionic part of the action. And the answer is, well, in general, there is now in the supersymmetric case there is a non-local and non-linear map, which maps the bosonic variables to others. This map depends on the coupling G, so it's what is called TG, in such a way that the correlation function in the interacting theory can be computed or is the same as the correlation function of a transformed operator, so where you just change the argument of your operator by the inverse, in fact, the inversely transformed bosonic fields, and evaluate it at the free theory. So the whole dependence on the interactions is being shuffled into this non-local transformation, right? And this should work for any bosonic operator. Now, if you work this out a little bit, just write down the measure, you see it means that this measure with the weight exponential of the action, full action, is expressed in terms of this, basically by making a change of variables here, phi to t phi. And here we can get the Jacobian by going back to the variable phi. Okay, and so exponentiating the Jacobian up here and separating in powers of h bar, you get two conditions. So this relation is equivalent to two conditions, order h bar, well, leading order of h bar. It just means that the free action, the free bosonic action, but for the transform fields, Tg phi is equal to the interaction, I mean, to the bosonic action, original bosonic action. It's called the free action condition. So here you have this the quadratic action, but in terms of the transform fields, and this gives you the full interacting action. And at the order of h bar, you get a condition that basically the Jacobian here, determinant of the Jacobian, should match the fermionic determinant, which is hiding here in the non-local part of the full action. Yeah, the fermionic determinant is here. So is basically an equivalent between the Jacobian and the what I call MSS, Matthews-Salam-Seiler determinant, which is a Pfaffian really, because we're dealing with Majorana fermions. So these two conditions have to be satisfied. And essentially what I did in my PhD thesis, consider an infinitesimal version of that and use that to integrate up to construct the map. As an infinitesimal version, just take a differentiate the relation, the defining relation, and okay, I don't need maybe walk through all the details. This you just use the defining property. You just differentiate. Well, there could be an explicit dependence of y on g, but the implicit dependence is here on the map. You use the chain rule, and then you go back from the free theory using the map. Go back to the interacting theory. Here's a g by going again to the variable phi, and here you have to do the inverse transformation. And so you see now the derivative of the correlator is given by a derivative operator acting inside the bracket. A derivative because here's an explicit derivative with respect to the coupling, but here's some kind of a functional derivation, okay, because of the chain rule. This is a variation with respect to phi. So this is a functional differential operator acting on our operator, and then this is the infinitesimal version of the map. And this R we call the coupling flow operator. And so, well, once we want to reverse the logic, somehow find this coupling flow operator and then exponentiate it to find the inverse map, and then invert that to find the map. So all these maps is, of course, there's just given perturbatively in powers of g. So it starts with the identity 1 plus something. So you can always formally invert it to power series. There's no problem with that. So two remarks before I come to the construction of the flow operator. But as I said, it is a derivation. This is very important because it means that its exponentiation, namely the inverse map, acts in a distributive way. So here's the derivation. On any functional y, it acts like a derivation. So when you exponentiate it, it means that when you act with a map on any functional, it's the same as evaluating the functional on the transformed argument. When you have a product, it acts on each factor. And it's actually interesting to rewrite this equation a little bit, to move the map, which was here was t inverse phi, move it on the other side of the equation. We have t here, and then differentiate again with respect to g. And then, well, you just use the chain rule a couple of times, and you get a nice and simple relation. You get this is 0 for any operator of y. So it means that this expression here must vanish. So this is basically, well, the operation of this flow operator acting on the map itself should vanish. So it means that the transform field is a fixed point of the flow operator. And that condition actually is much better for constructing the map. We just have to solve this equation. Okay, once somebody gave you this flow operator, you could just try to solve this differential equation and get the map itself, not going via the inverse. Okay, so I'll do that in a moment. But first of all, let me show you how you get the map. And in fact, there is a nice universal formula, which we only discovered this year, but could have done 40 years ago. Because this equation here is well, it's a standard equation, you know from quantum mechanics, essentially, how to do this. And the solution is given by a path-ordered exponential, where here you have just an integral over the coupling, integrating from the free theory up to whatever coupling you wanted of the flow operator, and then acting on the field phi. Well, you can of course write it in formally here as an infinite sum. It's instructive to expand the flow operator into powers of G. Okay, so the little r's are the coefficients. Well, they're independent of the coupling G, but these are the different coefficients in the power series. So each of these guys is a differential operator still, functional differential operator. And then one can actually evaluate this exponential here by giving the map also as a power series. And here over, well, this n is a partition, ordered partition of the number n, which is the power. So you partition n here, and then you have a different sequence of coefficient operators r and 1 to ns acting on phi with a coefficient that can be explicitly evaluated. This is related to the Stirling numbers, something very simple. And here's the beginning of the series. So here is, for example, if I had this flow operator and expanded in powers of G, I just insert it into this formula. And here's the first order, the second order, the third order. And you see the partitions of 2, the partitions of 3 in this formula. Okay, so this formula is very easy to write down to any orders. So the question then basically reduces to the question, when does such a flow operator exist and how to find it? So let me show you how to do this in scalar theories. If supersymmetry is realized off-shell, then there is always some functional delta, depending on fermionic indices, such that the derivative of the action with respect to the coupling is it's essentially the this is the last component of a superfield. So then it can be obtained by a super transformation of one last component of the superfield. Yeah? So you just need the penultimate component of the superfield, delta alpha. And so the derivative is expressed as a supervariation. In a Wessel-Miner model, it looks like that. And the construction is then simply, you just perform the derivative with respect to G. You get an explicit derivative on the Y. You get a derivative of the action that you rewrite as delta delta. And then you throw over by partial integration the variation, the supervariation on to the operator. For that, of course, you need to use the Susy-Ward identity. Yeah. Now we have an explicit expression of this flow operator, but you have to still integrate out the fermions. But doing that just contracts the fermionic variables, which are here and which are also in the supervariation. So you get a fermion propagator, okay, in the background of your boson. So this is the expression that you get. So this hook here means just the fermionic bilinear contracting the fermions. Okay, in the case of the massless Wessel-Miner model, for example, with this superpotential, the operator looks like that. And we can easily set up some kind of graphical notation for it. So in this case, you see there is a phi squared here in the end. So I don't distinguish really between phi and phi star here. Let me simplify the notation a bit. Just write phi. Then you have a phi squared here in the end, and you have a full fermion propagator, which of course can expand. You know, there are corrections, there are different orders of G here, and you can set up a set of Feynman rules and just get, you get a linear trees. So there's a tree expansion for the flow operator, and when you exponentiate that, you have this operator acts on itself in the exponentiation, and then you get not just ordinary trees, you get trees with where these fermionic lines are interrupted. So every fermion line is a spin, has a spin loop, in spinor space. But sometimes when this guy acts on itself, of course, you get a two-trace term. And then you get higher order things which are branched trees. So you get a branched tree expansion for this map. Okay. And you can, for example, look at simple correlators. Say, for example, here's the 2-point function. You insert this. So it can be expressed as a free field correlator of branched trees. Okay, so when you insert the different tree terms for the first and the second point here, and then you contract the free fields, the free bosons, just with the free propagators, and you get various diagrams which look different from the ordinary Feynman diagrams, but they have the advantage, they have the leading UV cancellation in supersymmetry already built in. So there's no pure fermion loop, and there's no tadpole on the bosons. This is already cancelled. It's automatic. Okay, the case of gauge theory is a really interesting one, but of course gauge theories are always complicated because we have gauge redundancy and they make our life hard. Well, the gauge has to be fixed, so some gauge fixing function has to be chosen, and then we get ghost fields, and the gauge invariance reduces to BRST symmetry. So here is a normal supersymmetry action for super Yang-Mills. Here's the gauge fixing term with some parameter psi, fermions, ghosts, auxiliary fields. I don't write. This is the field strength as usual. I scale it such that the coupling is here. And let's, for simplicity, take SUN as a gauge group. Okay, this is familiar. I will now be in D dimensions, so D-dimensional Minkowski space, and my fermions are my Rana, Gaugini, and the dimension of the Clifford representation I denote with R. Okay, so there are R component Majorana spinors, where of course this R depends on the space-time dimension. Now let's try to copy what we have done for the scalar fields. If I do that, I run into a difficulty. So if I do that with this kind of, where the coupling appears here, the first problem is that when I take the derivative of with respect to G of my action, it is not a super transformation of something. Because gauge transformation, so this somehow interferes with the differentiation with respect to G. So I can write it as a super variation of this guy, but there is some mismatch. There's of course first the ghost part, which is not captured by this, and there is the fermionic part doesn't quite match with the proper coefficient. So I still have something left of the fermionic vertex. So, and then the construction is more complicated because supersymmetry is formally broken by the gauge fixing. And you have to, the supersymmetric Ward identity has extra contributions which you have to take into account. And you use the BRST Ward identity. So to make a long story short, this is something I did in '83, 4 dimensions, and we generalized it last year to high dimensions. The result is good, but there is a multiplicative term in this operator. So here is the shorthand version of the flow operator. You see it's not just a super variation, there's also a Slavnov variation term, which comes from the ghosts. Well, which is some explicit expression here, but there is a multiplicative term which is not derivative, which is here. And this destroys the property that the map should have, right? So what do? Well, you compute this term. Compute it in a correlation function, and it's a little bit tedious, and you have to look at what gauge you choose. If you took the Landau gauge, it turns out that this thing can vanish, but it only vanishes when there is a condition on this coefficient. It depends on the space-time dimension and on the size of the spinor. And that condition is only satisfied in the critical dimension of the Yang-Mills theory. So this means that the Nicolai map knows about the critical dimension of super Yang-Mills theory. Only then does it work. Now there is another version. One could alternatively say, well, let's rescale the field. Let's rescale the gauge field to take the coupling outside, like here. So my tilted quantities are now rescaled, F tilde, A tilde, and the coupling is here. Now it's easy because when I take the derivative with respect to G, I just get the action again. And the action is a super variation of something. Okay, so I don't have this problem. So that's I already did in my thesis, but we reconsidered it in arbitrary dimensions. Well, reconsidered it this year. The problem with this is now here we need off-shell supersymmetry. I didn't make use of off-shell supersymmetry in the first version, but now I need off-shell supersymmetry. So I can only do it really in 4 dimensions and less. Here is the delta functional, so there's no multiplicative piece. Everything goes through. You do your, use the water identities, and you get the proper flow operator. So that looks all nice. It's given here explicitly. Again, Slavnov variation, super variation. The drawback is we want to do perturbation theory in G in the coupling. But if you do this kind of scaling, you see G equals 0 is singular. So you cannot set up a perturbation theory around G equals 0. In order to do that, we have to scale back to the original. Yeah? Go back to original unscale untilted A field. And then the flow operator in the original variables is related to the flow operator, which I just calculated by this formula. And you see there's a 1 over G. So that is dangerous. It looks like it's formula singular when you put set G to 0. But lo and behold, when you look at this expression carefully, you find that the leading order in the bracket cancels here. And everything is actually well defined when G goes to 0. So one gets an operator, a flow operator, which looks a bit more complicated. In fact, it's interesting in the fact that it has here as a functional variation. I'm now having it on the left for convenience. Here's a spin trace. Here the two, well, A star is just a combination of transverse and longitudinal parts of the gauge field. Here's the propagator, and here's a projector. It's an interesting projector, which is given here in terms of the ghost propagator, the gauge fixing. This projector is kind of a non-abelian projector. It is killed from the left by the gauge fixing and from the right by the covariant derivative. So it's like a generalization of the usual transverse longitudinal projector that you know from electrodynamics. And it guarantees, in fact, that the coupling flow conserves the gauge surface, hypersurface. So we don't flow out of our gauge hypersurface. So the upshot of this analysis is that in 4 dimensions, we can, using this method, we can do 4 and lower dimensions. We can do the map in any gauge, whereas in high dimensions, at this point, we have to resort to the Landau gauge, where we could, remove this multiplicative Z factor. And the explicit formula that I gave you before, this universal formula holds true just as well in the gauge case. Yeah, just to show you how the diagrams look like, let's for simplicity take the Landau gauge. And this is, well, an expansion. Now this is just a free fermionic propagator, and the little wiggly lines are the external gauge fields. The dashed lines is just the, well, it's the inverse Laplacian, inverse D'Alembert. These terms come from the ghost contributions. And you can plug it in and expand, and you get a branch tree expression. I've given you here the diagrams up to order G cubed. Of course, this hides a little bit the complexity of the expression, because there are still Lorentz indices hidden here. Well, because there are spin traces. Every uninterrupted spinor line has spinor indices. Yeah, this is a inverse Dirac operator, and we have to take the trace. When you take the trace, you get a lot of Lorentz contractions with the external indices, which I've not written here, of the gauge potentials. Yeah, here the gauge fields have Lorentz indices, and they can contract it in various ways. And so you get, in this case, I think here there's just one term, ordered G cubed, you get about 9 terms when you write it out. And the next order, G to the 4th, which was actually calculated by Hermann Nicolai with his student this year, is about 60 terms. So it goes pretty fast, but it's all implementable on a computer. It's all algorithmic, just combinatorics and graphs. So there's no obstacle in calculating this to arbitrary order. So in the last kind of 5 minutes, let me then come to what we did in the last paper, namely to apply this idea to the supermembrane. So this is something that Hermann Nicolai talked about last week here. well, remotely. And so I'm not going to spend much time on the supermembrane. He covered this mostly, but just to remind you on some of the salient facts, the maximally supersymmetric membrane, as invented in '87, can be obtained as an n to infinity limit of a particular matrix model, the BFSS matrix model, which actually, well, it's a bad name because it was not invented by these four gentlemen. It was invented 10 years earlier by Clausen and Halpern, and then investigated by Barker, Reinecker, Rittenberg, and Flume in Bonn in '85. And in fact, it was used by David Hoppe and Nicolai in '88 to regulate the supermembrane in a light cone frame. And only later it was reinterpreted as a second quantized picture for the membrane. So the main problem for the supermembrane is how to quantize it, because we don't have a free quadratic action about which to expand or which we use for a quantization scheme. So it's still an unsolved problem. And we propose to actually use this equivalence to the n going to infinity limit of this matrix model, which produces something that is called an area preserving diffeomorphism gauge theory. So it is a gauge theory for area preserving diffeomorphisms on the membrane. To use that, to use the Nicolai map to set up perturbation expansion. And okay, so the relation is the supermembrane by double dimensional reduction, goes to the 10-dimensional 2A string. And if you take the alpha prime to 0 limit, you get a 10-dimensional super Yang-Mills theory, which by Kaluza-Kleiner reduction to 0 dimensions or to 1 dimension, you arrive at this matrix model. This matrix model can also be seen as a model for ND0 branes in the 10-dimensional type 2 string. So there are various ways of getting it. And when you compare these theories, you see that in fact the coupling constant of this gauge theory, G, is proportional to the tangent of the supermembrane. So this would amount to an expansion in terms of around this low tangent limit, around 0 tangent. So in small tangent expansion of the supermembrane. So how does it work? Well, let's just reduce self-dual Yang-Mills from 10, say, to 1 dimension. So it's very simple. Here, the gauge fields. A0 is some auxiliary, will be some non-propagating field omega. The other, well, A1 to AD minus 1 is just called X. X will be the matrices in our matrix model. Well, omega also. A is an SUN index. Then we have the Majorana spinners become now SOD minus 1 Majorana. So for d equals 10, it will be 16 component. The covariant derivative, there's a time derivative that's the only one that's left, and the spatial part is just the adjoint action of the matrices. Okay, as given here. Now I choose the Lorentz gauge, which in this case, in this reduction, just means that this field omega will be constant. Omega dot is 0. That's all that remains of the Lorentz gauge. Then the the Lagrangian of maximal supersymmetric Yang-Mills reduces to this, I think, quite familiar Lagrangian of the matrix model. Here's the kinetic term for the matrices. Here's the familiar commutator squared potential. Here's the fermionic part, and this is gauge fixing stuff. Okay, so now I can use just my construction, or I can dimensionally reduce the flow operator I already have derived for Yang-Mills. Okay. Both lead to the same result. Here's my flow operator in this language. Now for the matrix model, you have a variation with respect to the matrices. You have, this is what remains from the propagator. Here's the inverse of the covariant derivative with respect to t. This is the propagator for the Gaugini. And here is some, well, quadratic expression in terms of the matrices. This comes from this term. And we have to take the trace over color, over spin. Again, we iterate this operator to construct the map. What is nice is that the auxiliary, the non-propagating A0, which was omega now, is killed by the flow operator. There's no variation with respect to omega. So omega is kept fixed by the map. And well, for example, in the temporal gauge, we can put omega to 0. That's the simplest gauge one can have. Only even powers of G, or odd powers in the flow operator, even powers in the map survive, except we are not sure what happens in order G to the 8, because then we can have a term where we have 9 powers, a plot of 9 factors of the gamma matrices, and that trace is non-zero. There's an epsilon. Okay, so something can happen there. We cannot rule that out. So here's a diagrammatic expression for the flow operator. These indices A, B, C, etc., are just the indices on the gauge, on the matrices that are here dressing the trees. And this is how for example, how the map looks like to order G to the 4. Let's just give an expression that we can calculate it. And it passes all tests, which is actually quite remarkable. If you think about it, look at the free action condition. You take this infinite tree, well, you take the t derivative, which kills the first line here, and square that. That is a horribly non-local expression. Each term in the sum is a non-local term. But they all cancel and reduce simply to this local quadratic or quartic term. Yeah. So that's very non-trivial. And the determinants also take the map, compute a Jacobian, you have to vary this with respect to x, which means that you differentiate away one of the leaves here and then short circuit with the original point. That gives you obviously loops, but usually loops with trees attached to it. But all these loops will cancel except for the pure loops, which have to match the fermionic determinant. And that also works. And that actually only works in the critical dimension, as one can check. So it is non-trivial, it only works for 3, 4, 6, and 10. Okay, so let me just only mention that in the ending equals to infinity limit, we get this area preserving diffeomorphisms. And so then the matrices become functions of the membrane coordinates, the spatial membrane coordinates. The structure constants get replaced by this, where this is a complete orthonormal function set of the membrane, some kind of harmonics. It's explicitly known for the sphere and for the torus. And the interaction now becomes encoded into this bracket, which is given here as a derivative with respect to the sigma coordinates. And so all these expressions now are in the limit go over to these to APD brackets. There are some subtleties, in fact, because the derivative there are derivatives in the sigma here in the interactions, and we need some point splitting, and there are singular factors in the end to infinity limit. So there's some problem. In fact, things don't cancel properly only in the critical dimensions they do, and the individual determinants don't exist, in fact, in the limit, but their combination does exist. Yeah. So again, a hint that the bosonic membrane will not exist in this limit, but the supermembrane makes sense. So the supersymmetry is necessary. And if you do this up to order G4, it looks like that. So it's a nested expression of these APD brackets appear. And well, this could be, again, computed to any order on the computer. And of course, what we want to do is we would like to use that to calculate things with the supermembrane. Well, for example, calculate correlation functions. Here is a Graviton emission vertex operator as being computed by Nicolai and Plevka a couple of years ago. And this is a complicated guy. It has also fermions in them, so we must actually be a bit more clever when we integrate over the fermions, there will be additional contributions to the map, but in principle, it should be doable. One should be able to calculate correlation functions of this guy using the Nicolai map in the low tangent expansion. So that's something we want to understand. Oops, we want to understand why there's the Lorentz gauge, Randall gauge is special, and maybe, as I learned from the talk by Skoltsov a couple of days ago, this kind of the structure of this iterated map, I mean, it has a bit of a flavor of what he showed in his L infinity and A infinity system. So it would be interesting to see, perhaps one can discover some trace of integrability in this construction. That would be, of course, very nice, because we would be competitive with all those people in the integrability business. Okay, thank you for your attention.
Thank you. Questions? Please.
But your operator TG as a sort of dressing.
Which operator?
TG, this.
The map.
The map, yes.
It's a dressing.
Dressing all the fields.
Yeah, it is. If you want, it's a deformation of a free theory, right?
But
it's
this composite states, I mean, this TG will behave like free fields asymptotically, do they?
Can you?
Yeah, these transformed fields behave as free fields asymptotically. Can you build up
asymptotically? Yes, I think so, because the first, if you can see it here, the first part is, or maybe I go to the gauge. Well, let me go back to the original simplest one here. You start just with the map. The first term is just phi itself, and then it starts with the propagator, right? So when you go, I guess when you, well, you have to integrate, of course. But well, okay, when you put this, take this point to infinity, I mean the propagators fall off, right? So the fall-off behavior of the propagator should help you to control these terms. We have investigated renormalization of this scheme. It is it leads. In fact, in the ages already checked that the coupling constant universality in gauge theory is satisfied. So you can also do the renormalization program using the map. So in principle, in perturbation theory, there's no problem. I don't know about the existence in constructive field theory or so. I have no idea.
Thank you for your beautiful talk. On the constructive side, you know that the gauge is plugged with a control of the ubiquity.
Yeah.
And so it's quantization, stochastic quantization. And do you think you have anything to say on that?
Okay, you refer to stochastic quantization of gauge theories. No, I don't see an immediate relation here because we don't look at a space with an extra time variable that defines the dynamics which asymptotes to the correlations or to the to the real physics quantum correlations.
And some time additional by stochastic.
Yeah.
It's some kind of Monte Carlo time.
Yes, I know. But this is here. It's just if you want, it's just the reformulation of the ordinary perturbation series. Yeah, I mean, you could. In fact, what we did originally, we didn't have this flow operator. Well, when I started this in 1983, we just used the water identities to reshuffle the Feynman diagrams, to rewrite the perturbation expansion, and only then later we learned that there's a systematic way of getting this. So I don't think it's just in this sense. It's much more conservative than stochastic quantization.
Yeah.
Usually in low-dimensional gauge theories, you have very bad infrared divergences. How do this show in this calculation? Is it?
Yeah, I think they will show up finally in the correlator of the free theory, because this is just trees. The nice thing is somehow that we code the interaction into something that is classical in a way, because it's just tree diagrams, and the loops come only in the final correlation or in the free theory. So this is ultraviolet, of course, but I think also of course the loops are also IR divergent, right? So I think this is the same problem. It occurs only in this final step. So it's much more difficult than in the free theory.
Okay, if there are no more questions, let's thank Olaf again for the nice talk. Yeah, and Alberto's talk will be about the Bfe Formalism and Palatini-Cartan gravity and corner structure.
Okay, so thanks for the invitation. Very beautiful place. I haven't been here for about 10 years, so it was nice to be back. And today we'll quickly tell you something about well, the Bfe formalism, which is a homological way of treating the reduced phase space of a field theory, and actually what happens on corners if you assume that your Cauchy surface, or more generally, has a boundary. This is based, when this part, the application to Palatini-Cartan gravity is based on work together with my former PhD student Giovanni Canepa, but how the whole formalism is based with the joint work with Palatiniov, Nicolai, and also with Michele Schiavina. So let me just put what I want to say in context. Somehow the idea is, suppose that you have some field theory, and let me consider the simple situation where you have just some Cauchy surface across an interval, so in case, for example, for a globally hyperbolic space. And well, when you quantize, say in the Hamiltonian way, you're supposed to associate to the Cauchy surface some Hilbert space, and then to the evolution some unitary operator. Now, if your surface has a boundary, or for example, I mean, it could be have a natural boundary, or maybe you just want to remove some point in your surface because you have some defect there, and then you surround this defect by some small sphere. So if your surface has a boundary for some very reason, or it could be a boundary at infinity, anyway, what you expect from several point of view is that to the boundary you should associate some algebra, some associated algebra, and then your Hilbert space should become a module for that algebra. And actually, you I mean, some refined way of understanding the Tia-Segal description of quantum field theory is that if you want to glue these surfaces along their common boundary, but what you should do is actually take the tensor product of the two modules over the algebra associated to the common boundary. And the classical level, of course, boils down to saying that to the surface you should associate a symplectic space instead of Hilbert space, and to the boundary instead of an associated algebra you should associate the classical counterexample, namely Poisson algebra. And I will come to some explicit example of how to get that through this Bfe formalism. Important examples where you see this boundary structure, for example, current algebras in 2+1 dimensional quantum field theory, in particular in Chern-Simons theory, or in general relativity, the BMS symmetries at infinity. Of course, this is not exactly what I'm discussing here. We're discussing actual boundary. So if you have infinities, basically what you have to do is to choose some compactification, some conformal compactification to transform the infinity into an actual boundary. So there is this additional choice. Okay, now to be concrete, let's start with a very, very simple example, electromagnetism. So suppose that you have electromagnetism on a space-time manifold, which is just some space surface sigma, or some space manifold sigma cross time line. And well, as you know, in the Newtonian description, the canonically conjugated variables are the vector potential and the electric field, A and E. So both are vector fields on sigma, and you have a symplectic form, which is just given by the pairing using the Riemannian metric you have on space sigma, and there is a constraint, namely Gauss law. Just the divergence of E should be equal to 0, and divergence is computed by the same metric.
So the physically relevant symplectic manifold is a co-reduced phase space. So namely, first of all, you consider there's some manifold of the vector fields A and D where the divergence of E is equal to 0, and then you model out these by gauge transformations. And this has an induced symplectic structure, and this is the correct space of initial Cauchy conditions. Now, you can interpret this quotient in two ways. As I said, well, from theory, that well, the natural way to do this quotient is just by gauge transformations. But I mean, there is also a symplectic way of understanding this, which also ensures that the quotient is a symplectic manifold by itself. And namely, is the following. So first of all, you introduced these functionals. So basically, introduce some Lagrange multiplier f for the Gauss law, the divergence of E equal to 0. Then you can recognize these constraints on manifold C, which was like the locus where divergence of E is equal to 0, and the locus where all these functions are equal to 0 for whatever choice of f. And this turns out to be, well, these constraints are first class. So, well, you can compute the Hamiltonian vector field that's simply computed here, and you recognize the gauge transformation for the vector potential just as the Hamiltonian vector fields of these constraints. And so, from this point of view, the reduced phase space is just the symplectic reduction or mass and Weinstein reduction for this system. Okay, in this talk, I will focus just on these, well, somehow kinematic parts of what is the correct reduced phase space. I will completely ignore the time evolution. So we forget space-time, we just work on this space sigma. Okay. For several reasons, it's better to reformulate the symplectic reduction in a cohomological fashion, following Bataillon, Frack, and Vilkovitsky. Well, the original reason is that typically this reduced phase space is very singular, so you don't really want to go to the quotient, so you prefer to give some cohomological way of describing it. There is an associated reason if you want to quantize, even if the quotient were nice, it would be usually a very complicated manifold, so it's easier to quantize the original space, which is usually some affine space, and then quantize the Bfe formalism. There are further reasons that I will explore in this talk, namely that this gives a very nice way to understand what happens at the boundaries of the sigma. So let me quickly review what is a Bfe formalism in the case of electromagnetism. So basically, you rewrite these functionals, right? That define the Gauss law, but now you transform the Lagrange multiplier into a Gauss. So now this becomes an odd variable. Okay, so this function C now has Gauss number 1, and it's a Grassmann variable. And you also extend the symplectic structure by adding a momentum to this Gauss. So the Gauss momentum B, well, I think of the Gauss as a 0 form, so its Gauss momentum will be a top form, and it has to be also a Grassmann variable, but it will have Gauss number -1, so that the symplectic form is Gauss number 0 total. Now, first of all, let me assume that sigma is no boundary. Then you can compute the Hamiltonian vector field of these functions. So this is not function of Gauss number 1 with respect to this symplectic form, which is even of Gauss number 0. So its Hamiltonian vector field Q will have Gauss number 1, and it will be odd. And you can easily compute it on the fields. So Q of A is DC. So here you recognize the gauge transformation in the Bfe formalism, whereas Q of the electric field is 0. And then Q of C is 0 because Q of the Gauss is 0 because I'm considering the Billion theory, and Q of the Gauss momentum gives you precisely the constraint. Okay, so you can easily verify that Q squares to 0, and this is equivalent to saying that the Poisson bracket of this function with itself using the symplectic fraction is 0. So this is called the master equation, the classical master equation in the Bfe formalism. And moreover, you can see here that Q gives you the ingredient for the reduced phase space. It gives you the constraint and the gauge transformation. And actually, the relation is simply that if you take the cohomology of this Q in degree 0, you precisely get the algebra of function on the reduced phase space. Okay, and actually, this is an isomorphism of Poisson algebras. Okay, so roughly speaking, taking the kernel of Q gives a gauge invariance, and taking the image of Q gives the Gauss law. Now, if sigma has a boundary, there are problems in computing the Hamiltonian vector fields, right? Because to compute the Hamiltonian vector fields, you have to take the variation of this action and recognize it at the contraction of the symplectic form with some vector field. But when you take the variation of this action, well, you will have to integrate by parts, right? So here there is some divergence. Okay, so you want to get a delta E appearing by itself, so you have to integrate by parts, and so you will get some boundary term, which by just Stokes theorem is just the integral of the normal component of E on the boundary times the Gauss C. Okay, so there is this extra term, and so well, there are several ways of well, getting the charges in electromagnetism just by considering this term. There is a better way to do this in the Bfe formalism, and we'll come back after. Well, this, I will skip this digression. This is just a nicer way of doing this using differential form, but I think I can skip it. And instead, I will consider another very interesting example. Instead of electromagnetism, I will consider non-abelian Chern-Simons theory. So Chern-Simons theory is formulated in 3 dimensions. So in this case, sigma is a 2-dimensional surface. And the field is just a connection on the surface. I just considered the trivial case, so the trivial principal boundary over sigma. So for me, the field is just a one form of sigma tensor with values in some Lie algebra, and this Lie algebra should be endowed with an invariant inner product. The Chern-Simons theory describes flat connection. So in this case, the Gauss law is just curvature equal to 0. And to implement this, you introduce, well, these 2 pieces. So introduce in symplectic form and the Bfe action. So the symplectic form is, well, somehow the classical part is just pairing delta A with itself using the invariant inner product on the Lie algebra. Oh, sorry, here I missed that there is also the part involving the Gauss and the Gauss momentum, delta B plus delta C. Sorry, delta B wedge delta C. Okay, so this is the symplectic form that describes this system, and then you introduce this function here. So the first part is as before, in this case electromagnetism. This is just the way to impose the constraints f a equal to 0. So C is some sort of Olaf Lechtenfeld multiplier promoted to be in the Gauss. But now, since the theory is non-abelian, you are also to introduce this term so that S bracket with itself is equal to 0, or equivalently, the cohomological vector field associated to this system squares to 0. So it's really the BRST operator. So basically, this term is responsible for the fact that we want Q applied to the Gauss C to be 1/2 C bracket C. Okay, and again, you can show that if the boundary is empty, you can get somehow the functions on the reducer space, which is like the modular space of like connection modular gauge transformation, as a 0 homology here. If there is a boundary term, when you do integration by parts here, you are left with the integral of the covariant derivative of C along the boundary, and this is something that well, should be taken care of. Okay, now let me describe our way of dealing with the boundary. So the idea is the following. So instead of, well, taking care of this extra boundary term, we just somehow consider a weakened version of the Bfe formalism. So namely, let me first of all summarize what we've seen about this Bfe formalism in the case when sigma is no boundary. So what we have some graded space for fields, which includes also, I mean, the physical fields, the Gauss momenta, and so on. We have a symplectic form of this space. So this symplectic form should have Gauss number 0 and be even. And we have some alt function S, which has Gauss number 1. Okay, and you assume that this alt function has Poisson bracket equal to 0 with itself. Okay, then you can compute the Hamiltonian vector field Q of this function, and this condition is equivalent to the condition that Q is equal to 0. So this Q is a BRST operator. Okay, and explicitly the way, okay, just to remind you how you compute or define the Hamiltonian vector fields of a function, the relation is here. Right? So Q is a unique vector field which contracted with symplectic form gives you the differential of S. Okay. Now this becomes problematic if sigma is a boundary. So of course this would be true in the finite dimensional case. Now we are in the infinite dimensional case. I assume this omega to be non-degenerate, but still there might be a function whose differential is not in the image of omega. So there might be no Q, and this is actually what happens if you have a boundary. okay, because of the boundary term. I mean, you should either extend Q to have some singular boundary terms, or say, or give up this identity. Okay, and that's what we do. We give up this identity. So what we do is the following. If sigma is a boundary, we retain the Q computed without boundary. This is anyway a nice BRST operator, is local. We retain the same S as we had without boundary. And well, we just check what happens to this relation. So what we realize is that if there is a boundary, IQ omega is no longer equal to delta S, but there is some boundary term. Okay, using better language, we can formulate things as follows. So we introduce a space of corner fields on the boundary of sigma. Call them corner because these are corners of the boundary of space-time. Okay, and there is some projection from boundary from fields on sigma to corner fields. Well, dually, this is just a restriction of the fields to the boundary, but here only some of the fields will survive. And you can rewrite this equation more intrinsically by saying that the contraction of omega with Q is the differential of the action plus the pullback of some one form alpha that lives over this space of corner fields. Okay, so this alpha now will be a one forms, and well, okay, didn't write the shift here, but we have Gauss number one because Q has Gauss number one. Okay, so this alpha will be a one form on the corners of Gauss number one. Corner fields of Gauss number one. Okay, then what you can do, you can take the differential of this one form, so you get a two form. So here you get a closed two form of Gauss number one. And well, you would like this to be symplectic. So for this to be the case, well, it's where you have to see, well, exactly what are the corner fields. It's not just all possible restrictions of boundary fields. There is some reduction involved. I will not enter the details. In typical cases, this is quite natural. So there is a nice, well, very simple way of getting the space of corner fields in such a way that this omega corner becomes non-degenerate. Okay, so now what do we have on the corner? So on the corner we have a symplectic form, which is odd now, and that goes number one. You can see that Q, the BRST operator, is actually projectable with respect to this projection. So there is a unique Q on this corner space of corner fields, which is also odd or Gauss number one and commuting with itself. So this is again a BRST operator there. And moreover, you can see that this Q is a Miltonian. So namely, when you contract this Q corner with omega corner, this is the differential of some function defined on the corner fields. Now this function, well, you see by degree counting, should have Gauss number two and be even. Okay, there is actually an explicit way of computing this corner function in terms of data on sigma. You just contract the symplectic formula on sigma with the BRC operator twice, divide by 2, and you immediately see that this is gives you this corner function. Okay, so I will skip this computation for the case of Yang-Mills theory. We described it before. And let me go somehow to the general structure associated to the corner, and then I will describe the example of Chen-Simons theory. Okay, so what do we have on the corner now? So we have, as I said, a graded symplectic manifold where the symplectic structure goes number one, and we have a function of degree 2, which Poisson commutes with itself. Now, this, okay, at least in the finite dimensional case, and under appropriate assumption, this works for the infinite dimensional case. Essentially, this means that this symplectic manifold is actually a cotangent bundle shifted by 1 with the canonical symplectic structure of the cotangent bundles. We explain why this is degree 1. And if you are in the situation where all the corner fields have non-negative Gauss number, you can actually choose the base here to be the body of the supermanifold. So these are the fields of Gauss number 0, and then there will be only fields of Gauss number 1 in the fiber. Okay, and then, well, this data just give you a Poisson structure on the base B. Okay, so this function of degree 2 in this language is just interpreted as a bivector field on B, and the fact that it Poisson commutes with itself is interpreted by saying that it's a Poisson structure. Okay, without this restriction on the Gauss number, you can still write your odd symplectic manifold, the shifted cotangent bundle of some submanifold, but this will be a submanifold that contains coordinates of several degrees. Okay, and so what you get here is a Poisson infinity structure, not a strict Poisson structure. Actually, even in this case, you might decide to choose B not to be the space of some manifold of Gauss number zero field, but something else, and so you will get some associated p-infinity structure with respect to a different polarization of the space. Okay, so let me discuss this case of Chern-Simons theory. They said that the Bfe action for Chern-Simons theory was here, so the term responsible for the Gauss law, Fa equal to 0, and this is the term responsible for the gauge transformation of the Gauss. Now, you see that, well, when you try to compute delta S, right, because you have to integrate by parts, you have a term here which is like sigma covariant derivative of delta A, right? When you integrate by part, this will give you the covariant derivative of C, which is the gauge transformation of A, but by Stokes theorem, you get a term C delta A on the boundary of sigma. And this is precisely this one form of Gauss number 1 that you get on the corners, okay? Okay. And then you can compute the corresponding to form. Well, you know what Q is, and you immediately see what it is on the boundary. So see on the corner. So on the corner, you only have A and C. So Q on A acts by gauge transformation, on C produces C bracket C. And so you see that the Hamiltonian function for Q on the corner is what you have here. Okay? You see, if you take the variation with respect to A, essentially you get C bracket C, which is the Q applied to C. And if you take the variation with respect to C, you get the AC, which is Q applied to A. Okay, so this is the corner function. You see, it's the degree 2. And now the idea that to interpret it as a bivector field, what you have to do is to say, okay, A is the coordinate on my base B, and C is just the momentum, which is interpreted just as a derivative. Okay, so the bivector field associated to this function is what I written here. So I split the covariant derivative dA into a term with D and a term with A. And so you have two terms here. Okay, one term containing A and two derivatives with respect to A, and one term that contains the derivative D and two derivatives with respect to A. Now, if you just focus on this term, this is a linear Poisson structure. So it's a Poisson structure on the dual of some Lie algebra. And the Lie algebra is, well, in this case, infinite dimensional. It's just the Lie algebra of G-valued zero form on sigma, okay, with a pointwise bracket. And then there is the additional term, which is just a central extension for this Lie algebra. So here you recover the Kac-Moody algebra associated to Chern-Simons theory just by this very simple exercise. Okay, now in the remaining time, let me just give you a sketch of what happens in the case of four-dimensional gravity using field binds. So this is called Palatinic Antiformalism. So let me just introduce this. So the idea is the following. So we are working on a four-manifold M that admits some pseudo-Riemannian structure, and we choose at the beginning some vector bundle E over M associated to the SO1 frame bundle. The condition is that this vector bundle should be isomorphic to the tangent bundle. So this is sometimes called the fake vector bundle. Okay, and in addition, this E is equipped with a fiber-wise Minkowski metric. Okay, so the idea is just to reconstruct the fluctuating metric just in terms of field bind. Okay, so this is a mathematical way of describing it. So the classical action is written here. So, but first let me explain what the fields are. So the field E is just an isomorphism between the tangent bundle and this fake tangent bundle. Equivalently, you can think of it as a one form of M taking values in the sections of this E. And well, with additional condition that should be non-degenerate, because you want this to be an isomorphism. And omega is just an SO31 connection. Okay. And well, this is what sometimes called the spin connection, but there is no spin here. So this is just the frame bundle connection. Okay. And well, if you choose a reference connection omega 0, the fluctuation A from this point of view can be just identified with a one form on M, taking values in the Lie algebra, but you can identify the Lie algebra with the skew symmetric matrices. So in this case, are just sections of wedge 2E. Okay. So here, you can now think of the fields as forms on M taking values in the sections of the stereo algebra of E. So we introduce this notation omega RS. This means R forms taking values in section of the R stereo power of E. So from this point of view, E is a 1-1 form and A is a 1-2 form. And the curvature turns out to be a 2-2 form. So this term here is a 4-4 form. So it's a top form both as a differential form as a top form on E. And so you can immediately realize that this can be identified with the density on M, so it can be integrated. Okay. The other Lagrange equations are here. If you take the variation with respect to omega, you get E d omega equal to 0. And if you take the variation with respect to E, you just get EF omega equal to 0. Now, the first equation is actually equivalent just to the omega E equal to 0, because E is non-degenerate. You can check that these two equations are actually equivalent. And the condition the omega E equal to 0 just tells you that omega is torsion-free. And so actually there is a unique solution, omega sub E. For a given E, there is a unique solution, omega sub B, solving this equation. And now if you plug in this solution into here, you can, well, through some computation, realize that this equation here is equivalent to Einstein equation in vacuum for a metric G, which is just a metric defined using E. So you just take the fiber-wise Minkowski structure here to pair E with itself, and you get a tensor on your manifold, which is the metric. Or in other words, this G is just a pullback of the Minkowski metric on the fixed tangent bundle by E. Okay. Okay, so this is how you recover Einstein's equation from this Palatini-Cartan formalism. Okay, so this is just very classical. Okay, now let me assume that our space-time is sigma cross R, and I assume that sigma is space-like. So here space-like simply means that there is a condition that A restricted to sigma produces a Riemannian metric. Okay, and so this is a condition on the fields. Okay, actually what I'm going to say is more general. I don't have to require sigma to be space-like, but for simplicity, let me focus to this case, which actually is more physical. Okay, so the fields that I need on sigma turns out to be, well, the restriction of the field by E, which is now, again, still a 1-1-4. So now is a 1 form of sigma taking value in section of E restricted to sigma. Well, I should restrict omega as well, which should be, you can think as a 1 form of sigma taking values in the wedge 2 of the restriction of E to sigma. But actually, this contains too many degrees of freedom. So that the 2 form I construct this way is degenerate. So actually, you have to mod out omega by some equivalence relation. The equivalence relation is here. You say that omega and omega prime is equivalent if they differ by a 1-2 form V, which is killed by the wedge product with E. Okay. Now the symplectic form of this space, or actually before taking this quotient, is just here. Is integral over sigma, so E delta omega. So you see that E and omega are 1 form, so these are actually a 3 form that you can integrate. And well, and this is in respect to E. This is in wedge 1, and wedge 1. So these sorry, not in wedge 2. So this is in wedge 4. So it's top in the form, so you can integrate. Okay, what are the constraints? Remember, so the Lagrange equation where the omega equal to 0 and F omega equal to 0. So these are differential forms. You can just pull them back to sigma, and you get these constraints over there. Okay. Now, the important remark is that, well, especially if you want to work with these constraints, it's better to get a different description of this symplectic space. So instead of working with equivalence class with respect to these relations, it's better to choose representatives by some section or some gauge fixing. And so actually what we showed with my former student Lukierski is the following, that you can fix a representative omega as follows. So we have this theorem. Pick arbitrarily one function on sigma, onto one section of E restricted to sigma, with the condition that this E should be nowhere 0 and time-like with respect to the fiber-wise Minkowski metric. And then the theorem is that for every class of omega, there is a unique representative that satisfies this condition, namely this epsilon n where d omega E is in the image of E wedged with something. Okay, this is a unique uniqueness condition. And the nice thing is that if you define now the symplectic manifold not in terms of quotient but in terms of this condition, it turns out that this constraints the omega E equal to 0 is now equivalent to E the omega E equal to 0. Okay. even well, would not be equivalent in general, but they're equivalent once you made this choice. And now what is nice is that, well, if you now introduce Lagrange multiplier to impose these constraints, you immediately see how to compute the Hamiltonian vector fields. So this is the advantage. Okay, and so it turns out, like, very quickly, the result, there is the Bfe action can be written this way. So you have the Lagrange multiplier promoted to gauss that are here. So there's one gauss C that imposes the condition E d omega equal to 0. And then you want to impose the condition EF equal to 0, but you split it into somehow the parts, that can be imposed by E and by epsilon n, that they form a basis of G. So you expand in this basis, and you see that the Lagrange multiplier can be interpreted as a tangential vector field and a transverse vector field. Okay, so you recover that somehow the structure, here the gauge structure, are gauge transformation and diffeomorphism, including also transversal diffeomorphism. So this part is what is called the Hamiltonian constraints in general relativity. And then, of course, there are additional terms involving the Gauss momenta, but interesting, it turns out that you just need the linear terms in the Gauss momenta, like in the BRST case, even though this is not a BRST example. Okay, and then what you can do, you can apply the recipe I gave you before. You can go to the corner, see what are the corner fields, and do the whole computation. The problem is that, well, there is a nice way of choosing corner fields in such a way that you get a nice close to form omega twiddle, and you get this equation, but this omega twiddle is still single, still has a singular kernel, so you should do some symplectic reduction, and it turns out that it's not possible because the kernel of these two forms turns out to be regular, really jumps from point to point, but actually jumps in the other direction, so it's something you cannot remove by restricting to an open subset. But still, the construction I presented before, you can still construct a Poisson infinity algebra associated to this data, even if it is not symplectic, because ultimately, to define the multi-bracket of the Poisson infinity structure, you just use the, well, Bornhoff's derived bracket. So, and you have them here. Okay, so you can define a Poisson infinity structure not on all possible functionals of the corner fields, but only on the function of the corner fields that are invariant under the kernel of the two forms. And you're done. And then, okay, so we can stop here, but just, I mean, you can reconstruct somehow this very complicated Poisson infinity structure. And well, there are some simplified cases. For example, if you set to 0 all the vector fields, you can very easily see what the Poisson structure is. And I don't know, my time is up, or?
Yes.
Yeah, okay, so I can reserve this for questions, or just let me tell you that there is a very interesting Poisson structure there. Okay, thank you.
So, thank you very much. Nice talk. And is there some question from the audience? Yes, Paul.
Just to help me contextualize your work, can you say some comments with respect to the previous attempts of Weinstein of quantizing gravity according to symplectic formalism?
You mean Weinstein?
Yeah.
Yeah. Well, he's working in the usual second order formalism using like Einstein-Hilbert functional, and well, he's trying to understand how to get the reduced phase space as a generalized Marson-Weinstein quotient. And I mean, from a geometrical point of view, there is nothing bad. You have a coisotropic submanifold of some symplectic manifold in infinite-dimensional case, and the reduced phase space is just a symplectic reduction. Okay, but what we would like to have is some sort of a momentum map, such that this reduction is given by zeros of the momentum map. Of course, you can expect this to be a momentum map with values in the dual of a Lie algebra, right? You see immediately that this is not the case. So you go to the next step. You want to have a generalized momentum map, which is just a map from your symplectic manifold to a Poisson manifold. Okay, and the problem is that well, so the idea was that, okay, he was trying to get to this and he got some obstruction. So the idea was like, you take this quadratropic submanifold, and his goal was to find some neighborhood of this quadratropic submanifold in the symplectic manifold, in which you can formulate things this way. And well, this didn't really work. So he came up with this notion of a Hamiltonian algebra that should describe this structure, but I mean, it turns out like not to be enough. And actually, well, in fact, the main problem is the Hamiltonian constraint, as usual. Also, geometrically, he was trying to understand this geometrically, that you think of your sigma, three-manifold sigma embedded in space-time. And well, you see that somehow the algebra that should be associated to it also transforms this sigma, I mean, changes the embedding of sigma. And this is basically what causes all the problems. Now, there is some recent work, I think is not published yet, it's not even finished yet, by, Weinstein, Bloman, and also Lukierski, trying to put these two approaches together. And the idea is that actually you can use, well, not the Bfe structure described here, but the Bfe structure for the Einstein-Hilbert formalism, and put it together with what they have. So the idea is that basically you extend your quadratropic submanifold by adding some nilpotent direction. Somehow you reinterpret this BRST operator in terms of some nilpotent direction. In that context, you can make sense of Weinstein's program. But of course, it's not really in the sense of ordinary manifolds. You really have to use nilpotent coordinates.
Some more questions, or maybe some remote question? No, if not, thank you, Alberto. Yeah, our last speaker is Thomas Krajewski. Hi, Thomas.
Hi, Thomas. Do you hear me well?
Yes, we do. We do.
So let me
share
the screen. And
yeah, perfect. Perfect.
Not yet perfect. I just put the presentation mode. Is it better? I think.
Yes.
Okay, so let me first start by expressing my gratitude to the organizers. And my apologies also for not being here, because my initial plan was to be here. But unfortunately, there have been many duties at my university which piled up, and I was not able to really come for 1 week, and coming for 2 days is not what I want to do. So I took the opportunity to give this talk by Zoom, and hopefully I will be able to come back at some later conference in Corfu, because I've always enjoyed the ambience of this conference and the discussions with multiple people. So my talk is a short glimpse into the loop vertex expansion. So it will be slightly short, I think, but I'll try to convey most of the information. It's a joint work with Vincent Rivasseau and Vasily Zazonov. I think Vincent is here. I heard him a few talks ago. Well, let me start with the motivation. So the main motivation for what we did is divergence of the perturbative expansion in quantum field theory. So usually in quantum field theory, you start with a functional integral that you write that you expand over Feynman graphs, and this expansion is constructed step by step using the big theorem with multiple interpolation of integrals and summations, and at the end you obtain the perturbative expansion. If you take the logarithm of the partition function, then you sum over all the connected Feynman graphs, which is usually what you are interested in. And it turns out that this perturbative expansion is in fact a divergent power series. So why is it a divergent power series? First of all, it's known since long times in physics that this must diverge. It's a famous Dyson argument for the perturbative expansion in QED. in a more mathematical statement, suppose that this power series was convergent. Then the partition function, or the free energy log of z, would be an analytic function of the coupling constant g around g equals 0. So it would also make sense for g strictly negative, so a negative real number, which is impossible on physical grounds, because for g a strictly negative number, that this term is going to be negative, but then plus, then positive in the exponential, and the theory is nonsense, because the integral is really badly divergent. And from a physical point of view, you can look at the argument of Dyson, which expresses the fact that the vacuum is not going to be stable against pair creations when you have a strictly negative E squared in QED. So this power series cannot be convergent. And in fact, it's analytic, but in a domain whose boundary includes the origin. So if I can be a bit sloppy, on the right of the origin, it's analytic. On the left of the origin, so in the negative real axis, it's singular. Now, it doesn't mean, of course, that this perturbative expansion is useless, because it has been used in physics for more than 60 or 70 years. And it's definitely useful, but it's useful only as an asymptotic series. So it's going to give you a good approximation of the fundamental functional integral whenever it exists, as the coupling constant goes to g goes to 0. But if you want to work at fixed g, then at some point, after adding more and more terms, then the series is going to diverge. So the result is going to be nonsense. Okay, so the origin of this divergence is in fact twofold. It goes back, it's obviously due to the fact that if you want to gather the terms of a given order in the coupling constant, then the prefactor is roughly speaking of order of factorial n. So it means that you sum here the Feynman graph of order n, so with n vertices, then this is going to behave like n factorial. This comes from the fact that you have two reasons for that. First of all, you may have too many graphs of a given order. So even if the amplitude, say, is a kind of constant, then as you count the graphs, then you have too many graphs because they grow like factorial n. This is called the instantons. I will explain you in a couple of seconds why. But there is also another problem, which would be the fact that the amplitude of a single graph viewed as a function of n also grows too much, because there are graphs whose amplitudes are too large. This is called Renault Balance. So usually one can deal with those problems, especially when there is a minus to the n in front of the factorial. Then there are oscillations, and those oscillations lead to the possibility of doing a Boyle resummation. But this Boyle resummation can be singular at some point, and the singularities in the Boyle plane corresponds to classical solution of the equation of motion for that action, and these are called the instantons, or other singularities that come from the fact that some amplitudes are too large, and these are called renormalons because they are ultimately related to renormalization. And that's a very different, there are two very different problems, and in the sequel we will only consider the first problem, because we will not work in a quantum field theory, but we will rather work in a matrix model. Okay, so I come back to the presentation. Now, our work is based on something which is called the loop vertex expansion. It's an idea that goes back to Vincent Rivasseau more than 10 years ago. Here I put the reference. So in principle, once you have the slides, if you click, yes? There is a problem?
We don't see slides.
You don't see the slides?
Okay.
Okay, so let me, in the presentation mode, here you see the slides?
Yes.
Okay.
Yes.
So this idea goes back to Vincent Rivasseau more than 10 years ago. So in principle, once you have the slides, if they are on the website, you just click here and then you'll go to the archive. So the idea is not to expand over graphs, but to expand over trees. In fact, we start with a partition function and we will expand the partition functions over forest. So what is a forest? A forest is just a disjoint union of trees. So it's a graph without loops, and it may not be connected. But this is okay for the partition function. Once you take the logarithm, then you expand over trees, because taking the logarithm of something which is expanded over disconnected objects usually gives us a sum over the connected components. So the first step will be to expand the partition function over the forest, and then as a consequence, its logarithm will be a sum over trees. Of course, when we do this, the price we have to pay is that we do not get a simple power series expansion, because the contribution of each forest or of each tree is still a complicated function of the coupling constant. I'll say more about that in a moment, but what we have gained is that this expansion can be convergent. Why? Because, in fact, if you count the number of trees of a given order, then you find something that grows like a power of the order. So the number of trees is, roughly speaking, of the order of kappa to the n, modulo some polynomial in n. While the number of graphs of order n is, roughly speaking, of the order of factorial n. So, of course, if you have a power series whose coefficient is factorial n.
Something wrong, you are sharing a different slide or screen.
I don't understand what's happening.
It didn't move.
Sure. Okay. So I do it this way. It's not nice, but then you see the slide combinatorial approach.
I see. Yeah.
Okay. Okay. So let me stick to that. So the number of trees grows like a power of like a power, while like a geometric series, while this grows like a factorial. So it's obvious that a power series whose coefficient is like a factorial is not going to converge. Its radius of convergence is going to be 0, but in that case, there is a chance that radius of convergence is non-zero. But this has to be supplemented by also a bound on the corresponding amplitudes in order to ensure the convergence. And the typical bound we are expecting is of this type. So it's bounded by another constant to the power n, and then the modulus of the constant of the coupling constant. So one should be aware that this constant could depend on the argument of the coupling constant. It will not depend on the modulus of the coupling constant, but on the argument of the coupling constant, because for sure our power series expansion could not be convergent on the left of the origin, because we expect that for negative G, there is a divergence of there is no way to define the partition function or the free energy. Okay, now a first question that arises is how could this be related to the ordinary perturbative expansion in power series of the coupling cluster? It's simple. You just have to take that expression or that expansion, which is, as I said, a non-trivial function of G, and then further expand it into a power series in G. And then you collect everything. Combinatorially, here we have a sum over trees, but the fact that we have a sum over tree and that we expand the amplitude of the tree in powers of G is just adding loops to the tree. So you start with the tree, and then as you expand, you add extra edges on the trees that in fact form loops. Now, this is very nice. I'll try to explain it more in detail how you get to formulas of this type in the following slides. But before that, I have to confess that I'm not going to apply this to quantum field theory because that remains largely an open question. But I will stick to random matrices where it provides some interesting results. The question of quantum field theory is still open. There are some results by Vincent Ribasso and Zhitao Wang, but for quantum field theory like the 5-4 theory in dimension 4, well, this is of course not done because we know that this theory is kind of sick. Okay, so let me just introduce in one slide what are random matrices and why we are interested in. So let's say we are interested by this integral over n by n matrices. So n is the size of the matrix, m is a Hermitian n by n matrix. So I start with the exponential of that. That will be a replacement for the action. This is the quadratic term, this is an interacting term, and I'm interested in the partition function, so the logarithm of that quantity. And there is a perturbative expansion for random matrices. It involves ribbon graphs, so double line Feynman graphs, because in fact, if you look at a simple interaction like trace to the m cubed, you can write it this way, and then you see that the vertex has an extra structure of double lines. The edges are all double lines because they correspond to the two indices of the matrix. Okay, and so the Feynman graphs are in fact ribbon graphs, and for ribbon graphs there is a well-defined notion of Euler characteristics or genus, because in fact it's dual to a triangulation of a two-dimensional manifold just by writing the 3-point vertex here as a triangle. Then when you construct the Feynman graph, you lose the triangles. This explains the notion of genus. It's going to be the genus of the surface. It can also be expressed very simply using this combinatorial formula: vertices, edges, vertices because there is an n here, edges because there is a 1 over n in the propagator, and faces because every face here is going to produce an index, a factor of n by a summation over the index n. So random matrices are used in various areas of physics. Let me just mention a few of them. It was introduced by Wigner and Dyson in the study of heavy nuclei, but it also appeared recently in the work of Stanford Witten and Sarah Schenker and many other people in the formulation of JT gravity in the so-called Schwarzian limit. In that case, you interpret the matrix as a random Hamiltonian, but in a second type of approaches, you use this topological expansion as a large n expansion, either in QED or in two-dimensional gravity. So let me present the main result. So the main result is that this partition function is going to be a sum over trees. And this sum over tree is going to converge in a so-called Pac-Man domain, which is that domain. More precisely, for every epsilon, so epsilon is a measure of the opening of the angular sector on the around the negative real axis. So for every epsilon, we will be able to find a eta, which is the size of the maximum size of the Copley constant, or the radius of that circle, in such a way that in that domain, we have a convergence of the power series, which therefore defines an analytic function of G. And this can be done independently of the value of n. This is very important because that last point allows us also to handle the large n expansion. Okay? Of course, if you want to reduce the opening here, so if you want to reduce epsilon, so if you want to close towards the negative real axis, then the radius eta is going to shrink because you are not allowed to touch the real negative axis. Of course, you can move some contour integration, then you can move the negative real axis to another place, but you will nevertheless always obtain a cut. That result can be found on in two papers by Vincent, Vasily, and myself on the archive. The first paper deals with a complex case, and the second one, more recent, deals with the Emission case. Okay, so I'll try to explain the proof of that result in the remaining time. It relies on two arguments. So if I go back to the presentation here, so first we have to expand the partition function over trees, and then we have to bound the tree amplitudes. So expanding the partition of function over trees is a rather combinatorial construction, which uses the so-called forest formula of Abdeselem, Bridges, Kennedy, Rivasso. So this formula is kind of a generalization of the fundamental formula of integral calculus, which is just expressing phi of 1 minus phi of 0 in terms of an integral of the derivative of phi from 0 to 1, to a slightly broader setting where phi is a function of n minus 1 over 2 variables, which I call xij. So I and j can take the value from 1 to n. I assume that it's ordered in the sense that I is less than j, or that the function is symmetric in changing I and j. And of course, I don't take into account I equals j. So for n equal 2, then you have just one pair, which is x12. For n equals 3, you will have 3 pairs, x12, x13, x23. So in general, let's assume that we are given this function phi, which is assumed to be smooth enough so that everything works fine. And the xij take values from 0 to 1. Ultimately, we interpret this n minus 1 over 2 variables as associated to edges between n vertices. The result of the formula is that phi, evaluated when all the edge variables are equal to 1, is in fact a sum over all the forest you can construct on n vertices of an integral over all the variables associated to the edges of the forest. So if you consider a forest having only, say, m edges instead of n over n and minus 1 over 2, then you have only m integrals. I'll explain on the two examples later. And then there is this partial derivative with respect to all the edges which are in the forest. And then you evaluate the partial derivative on some number, Vij's, which are functions of the Uij's. And Vij is, in fact, I and j are labels for the vertices of the forest. And it's, in fact, the infimum of all the variables, UKL, which are the integration variables, along the unique path from I to j in the forest, if it exists. If the path does not exist, then it's going to be 0. Okay, so the formula may look complicated, but it's not so complicated. Let's see how it works on for small values of n. So suppose I take n equals 2, then we have 2 vertices, 1 and 2. There is only one variable, which may correspond to the edge, to the unique edge joining the 2 vertices. And we have 2 forests. First, the empty forest, and then the forest with 1 edge. For the empty forest, there is no path, so all the variables are set to 0, as there is no partial derivative because there is no edge. So in fact, you have phi of 0, okay, which corresponds to the absence of the unique possible edge here. For the next case is to have 1 edge in the forest. So you have 1 partial derivative with respect to the unique variable x12, and it's associated with a variable t12, which is the integration variable here. And then you recover basically the fundamental formula of calculus. It's very obvious. Now, let me just show you the next case, which is more interesting. So in that case, you have in fact 7 forests. First, you have the forest without any edge. So this gives us, as usual, phi of 0, 0, 0. Then you have the forest with a single edge here. So there is a variable u12. There is 1 partial derivative with respect to u12. So like here, I'm sorry, I missed the index. So it's not 1, 2, it should be 2, 3. 2, 3 here, 2, 3 here. So I'm sorry for that, but I think you can correct by yourself. And then the 2 other edges here are absent, so it's going to be 0 and 0. And you have 2 more forests with a single edge, because you can put the edge here and the edge here. So this is the pair here. Next, the forest with 2 edges. So let's see here if it's correct. It's 1, 2, and 2, 3. So this one is correct. I take 1 edge here and 1 edge here. So I derive with respect to x12, x23. I put the variable u12, u23. And now for the remaining variable, I have to take the infimum between all the variables associated to the path that joins 1, 2, 3. So the infimum between u12 and u23. And there are 2 permutations, just by taking the 2 other pair of edges. Now, the graph with all 3 edges is not a forest because it contains a cycle, so it's excluded. Altogether, you have 7 terms, and then if you have some, say, 20 minutes, you can express all the integrals and then check that everything cancels down, and what remains is 5 of 1, 1, 1. And then it goes to higher order. Now, let's see rapidly how this comes into the matrix integral. Suppose that I have a general matrix integral of that type. I integrate over emission matrices. I have the kinetic term here, and here I have a potential. And now I would like to use that forest formula to generate a sum over forest and then a sum over logarithm, a sum over trees by taking the logarithm. So first, let me start with that integral. I expand the potential in that form. Now, instead of having an integral over a single matrix A, I will replace for fixed n that by an integral over n independent matrices. The potential, instead of being V of A, so here, sorry, again, typo, it's a factor of n here. It's raised to the power n. Then instead of having an integral, instead of having just VA to the power n, I write it as VA1, VA2. And I keep in my head the constraint that all the A must be the same matrix, in fact. So in that case, it's perfectly equal. So that constraint, I write it by using this strange kinetic term with Cij minus 1 is, say, a given matrix. And I have to set the matrix Cij to be 1. Not the identity matrix, but the matrix with all entries being equal to 1. And the fact that I set this coefficient matrix Cij to have all entries equals to 1, in fact, sets Ai to be equal to Aj. In fact, it's a kind of inadapted notation, because in that case, of course, the matrix, the inverse matrix is not well defined. But by taking the limit, it's going to act like a delta function. You can express that, for instance, using Gaussians, if you prefer. Now, once you have done that, you will say, okay, I will take this matrix here as a free parameter. In fact, only the off-diagonal terms are varied. The diagonal term will always remain equal to 1. And then this is going to be a complicated function of the n minus 1 over 2 variables, which are the off-diagonal terms of that matrix. And I'm going to use the forest formula. And then this is going to be a sum over forest for some amplitudes here that depends on the potential. And finally, I take the logarithm and I get a sum over trees. So this is the way the sum over trees appear. But the amplitude remains a rather complicated formula. So how do you find the bounds on the amplitude? So the bounds of the amplitude are
almost over. So, yeah.
Okay. So the bounds on the amplitude is obtained by a change of variable in the potential. So this change of variable is in fact a change of variable which is dictated by something which is called the Morse-Paley lemma, which I will come back in the last slide. It tells us that if you have a functional like that, you can always, by a change of variable, reduce it to a quadratic functional. So here is the explicit formula. But if you do this, in fact, what you are going to have here, I think I have another typo. It's a 2p. I'm absolutely sorry for that. Now, if you do this change of variable here, of course, the two are equivalent. But since we are doing an integration, you have to take into account the fact that there is a non-trivial Jacobian. And the Jacobian can be computed as the trace of the log of dm over dA. I put here a trace tensor product because, in fact, due to the matricial nature of the change of variable, in fact, when you modify a matrix, you modify it on the left and on the right, and then you are taking the trace in the tensor product of two identical matrix spaces. If I want to be more explicit and express A in terms of M, which is express M in terms of A, which is useful, then I have to use the so-called Fuchs-Catalan function, which is a function T satisfying this equation, and which we assume holomorphic, except that it has a cut on the on part of the real positive axis, because when Z is positive for Z large enough, it's clear that this series will diverge. Now, using this explicit form, you can derive some bounds based on the analytic properties of the Fuchs-Catalan function. And one question that can arise is, what did we gain by doing something so complicated? So a change of variable, we had a very simple interaction here, which is just a polynomial, and then we perform a change of variable and we obtain this complicated interaction, which is non-polynomial and not very explicit, because we have not derived an explicit form for T of Z, and it uses a double trace, so that may look not so useful to do something like that. But a very good point about that change of variable is that we have written the interaction, the effective interaction, like a logarithm. And when you do the expansion, then you will get the derivative of the logarithm, which are resolvents. And those resolvents are very easy to bound. And those bounds will establish the theorem. Okay. So I think I'm going close to to the end of my time. So altogether, this produces a proof of the theorem I have stated. So let me come back to the theorem. The theorem is that this is a power series expansion. This is not a power series expansion, it's an expansion over trees. And this expansion over trees is convergent. And the proof is based on the two ingredients, Forest formula and a bound provided by this change of variable. Now, let me say a few more words using towards quantum field theory. In fact, we would like to apply the following technique to quantum field theory. So in quantum field theory, we should deal with this action and the functional integral over this field phi. So, of course, if you stick to a purely combinatorial level, you can still use the Forest formula, and you will get a general formula, which is at that time only of a formal nature, because then you have to propose some bounds on the amplitude. A possible idea, which is inspired by the previous technique, is to find a suitable change of variable in such a way to generate an interaction which is of a logarithmic type and which could be possibly bounded in an easy way. Now, this can be done using the famous Morse-Paley lemma. So the Morse-Paley lemma states that if you have a given functional in a Hilbert space, around a critical point, then it can always be reduced by a change of variable to a quadratic form. So S of phi, for instance, is the action here, can always be written as the scalar product of chi of phi with itself, where chi of phi is a suitably found functional of phi. And the scalar product is in fact given by the kinetic term. So we interpret the quadratic kinetic term as a scalar product of chi with itself. So if you do this, you'll get an effective potential, which is of this type, which can be explicited. So everything can be explicited. But the difficulty is to find suitable cutoff independent bounds, because we are doing with path integrals. Therefore, we have to introduce a cutoff if we want to make that well-defined, at least at intermediate stages. And finding cutoff independent bounds is not something which is too obvious at that point. A first step would be to consider a matrix model with a kinetic term. So instead of having trace of m squared, we would have trace of k m squared, where k is a positive definite matrix, which will play the role of the kinetic term. This is typically the situation of the Gross-Vulkenaar model formulated in the matrix basis. It has been studied in the 2D case by Vincent Rivasseau and Zitu Wang in that paper, not using that technique, but using the intermediate field techniques. But if we want to, we can possibly also try to work out using this technique. The Gross-Vulkenaar model has been constructed in some sense by Vulkenaar and his colleagues, and we know that this is doable. And it has interesting, nice UE behavior, which makes the expansion likely to converge. But at that point, I have to say that nothing has been done, at least using that techniques, and probably there will be something in the future on that topic. Okay, so I think I'm done.
Thank you. Yes. So, question? Yes.
This is not a question, more a kind of remark. This change of variable reminded me of the Nicolai map. It is done for supersymmetric Yang-Mills theory, but I saw similarities with the Nicolai map. It's also some similarity by the Nicolai map and our approach.
Did you hear the question, Thomas?
That was not a question. That was a comment. But I can comment on the comment. But well,
yeah. Oh, wow. The question is whether you want to say something to this comment. Okay. If there are no further questions or comments, so let's thank Thomas again. Yeah, we can close our